think we're recording now.
Oh, we're recording now? Okay.
32 gigs.
All right.
Thank you.
So what did we miss?
Not sure. I think we're good.
Okay, well anyway, I'm sure I was blabbing on about that being a Markov chain. And so, but here's a big step that you can't forget, that we're imposing that the nominal behavior is random. So nobody has a Markov pool. You know, like I said, oh, it's Markov, but it's deterministic. You know, you've got 8 hours of cleaning, 16 hours idle. 8 hours cleaning, 16 hours idle. In my case, it's 12 hours on, 12 hours off. I'm going to impose randomness. So instead of deterministically turning on after 12 hours, after, say, 6 hours, there'll be a small probability of turning on. There'll be a probability of half of turning on at 12 hours, and then a small probability, you know, that I'm still on after, you know, after 18 hours. Now, that's quite a lot of slack. So, you know, you're allowing anything from 6 hours to 20 hours or, you know, or 18 hours of cleaning per day. Why not? Who cares? Do you think anybody cares? I mean, you know, this is all to keep algae from growing and stuff. If you have 6 hours one day and 18 hours the next, it's just not going to affect anybody's quality of life. And if it does, well, then I'll modify it. You know, if some algae specialist tells me that this is too broad, then I'll move it over. I mean, you know, big deal. So then basically, you construct all these different switching curves depending on the value of zeta, and this is through some optimization algorithm, which I can't describe. So this is the output of an optimization experiment. And so when zeta is 2, you can see this goes way up. There's a higher probability of turning on. And when zeta equals 4, you're basically saying, damn it, turn on. You're screaming. And similarly, it's not as extreme going this way because of the way it works. So basically, what happens is you're screaming. When zeta is big, you're screaming to turn on, and if you're already on, you're screaming, stay on. That's what's going to happen. But again, the precise way you get these curves, I'm not going to explain. All right, so that's just an example of a randomized policy. Clear? Yeah, I mean, you could draw these curves. You could just have fun and draw curves. I'm sure it would work well. All right. Now, get a load of this. So this is a randomized policy, and this is tracking a Bonneville Power Authority reference signal, the balancing reserves. And you notice there's something? Not a million pools. It's 20. So if you guys did your priority stack business, that's what you would get. You know. And I know when I presented this at Berkeley years ago, Praveen Varaya, who's like been very closely involved in all this stuff, he said that's fake data. And it took me so long to convince him, Praveen, it really isn't fake data. I can show you the code. He just didn't believe it. You know, this is the outcome of an experiment with a very random system. It's just that there's feedback. Okay, I mean, there's you know, you've got 20 pools. And you have 1 over n, or 1 over 20. So that's the power consumption of the teeth pool at time t. And you're feeding that back. And then you have a compensator here. All right. Now to get that beautiful tracking, what do you think we use for a compensator? So basically, we had our 20 pools, all right, and we measured the average power consumption, which we wanted to track some reference signal, you know, which would also be normalized too. But we wouldn't. The averaging is just because the mean field model point of view. Really, it's the sum we care about. But you know, who cares about constants? So what I heard somebody say it. What would? Yeah, you'd integral control, just flat integral control, nothing fancy, and you get beautiful tracking, and it's robust, and yeah. 20, you know, and so you're 300,000, which is less than half of the pools in Florida. It's perfect. It's too good. it's just too, nobody gives a shit about perfect tracking like that. I mean, I don't think anyone cares. No generator can do that. Batteries can't do that. Nothing can do that but loads. But nobody cares. You don't need such accurate tracking. It's a miracle, though, isn't it? You know, I mean, this blew my, I couldn't sleep, you know, when we saw these plots. Yeah, so again, you need feedback to get such good tracking, but we don't need such good tracking. So I bet you can break this loop. You know, I bet you can get away with just one way, you know. Okay? Yeah.
Does it, the pool pumps are like artificially modules?
Yeah, this is all this design where every pool receives the same signal zeta, and they have this randomized decision rule, which is portrayed right there. You know, the P minus is symmetric. You know, it's what was your question?
So I guess how closely does that moderate the real pool pumps?
Oh, it doesn't. Who cares?
Okay.
Yeah. No, it doesn't matter. You see, pool pumps, the cleaning cycle of 12 hours or 8 hours is just so arbitrary. You know, I mean, if somebody says I want a minimal number of cleaning hours per week, you know, then you'll impose that. You know, you'll put in another feedback loop. There'll be sort of you know, there'll be some other thing to make sure you get minimal cleaning. Yeah.
It's interesting to point out when zeta equals 0, you've still changed the number.
Yes, and you have to. Yeah. So if you kept zeta equals 0, if you made it normal like my house is today, everything would fall apart. I couldn't do this design. I couldn't get these beautiful results. I need this family of functions to be smooth, as we'll see today. You know, and the only way to make them smooth is to create randomness in the nominal behavior. Yeah.
I'm having trouble see. So
Yeah.
I get it with the pools as the plan, but what about with the grid as the plan? So how are you, I guess, like, you're talking about transmission.
Yeah.
So
Yeah,
what are you looking at?
Yeah, so this would be, you know, in Jupiter, Florida, and FPNL already knows every pool, and they already have communication with every pool. So they could do priority stack maybe too, I guess, which is too bad. But they don't. They have their own reference signal based on the, you know, totality of Florida, based on tie line errors, based on frequency, based on all those things. So they have this R that they'd like to track. And maybe they know what pools can do, so they condition this R. So they're only asking the pools to do some low frequency part of their needs. And they have a PI compensator here, or integral control, and close the loop. I mean, no. And I'll show you more, I'll make this more concrete as we go. All right. Okay, so let's go back to, so I'm basically helping you with the homework again here. So this is the homework problem you're looking at now. State 1 in this fake water heater means I'm on and consuming power. And I stay on with probability alpha. I'm sampling every minute. And I turn off with probability 1 minus alpha. Why do I love mean field models so much is suppose you had 10 to the 100 water heaters. How about 10 to the 1 billion or whatever? This mean field model we've been talking about, this histogram, is dimension 3. You know, it's always dimension 3. It doesn't matter how complex, how many loads there are. The thing you care about is always just 3-dimensional. In the pools, it would be like 40-dimensional. You know? Okay, and so basically, let me remind you what that is. It's right there. Okay. So you have all these different states. In this case, only 3 states. So x equals 1, 2, or 3. You know. All right. And that sum is just how many states, you know, are there that are in this state x. So if x equals 1, how many loads are on? All right, and then divided by n is because it's a histogram then. So you're talking about proportions, you know. So, so basically, if you let n go to infinity, you would get a limit, and it would evolve according to this really simple equation, you know. That's what something you can prove, and it's I hope it's clear intuitively. You know, you're saying I'm looking at I sum over all possible states, right, and look at what is the proportion of mass that's in state I, and how much of that will be transferred to state J. What proportion will be transferred? Summed over all I. That's all it is. So let's walk through this slowly for this example. So basically, let's do an experiment where I start off with just 100 loads. That's very small, you know. It's bigger than 20, but actually, for something so extreme where it's for just a small amount of time, I'm consuming a lot of power, and then for a long time I'm off, you need more loads to get a reasonable, you know, solidarity between the mean field model and the approximation. Okay, so we basically then, if I look at what I've looked at here, is I haven't normalized. So there's a bar chart there. Instead of I didn't divide by 100. See, I avoided the division because it's more intuitive. Okay, and so here I've got the initial condition for the Markov, the 100 Markov models, all of them starting on, and I initialize the mean field model to be supported solely at 1 as well, but then I've multiplied by n, which is 100, and I'm looking at a bar chart for that. You know, so this really, if I just looked at a bar chart for mu k, it would be 1, but I've multiplied by 100. All right.
Are you saying in that case is that all the 100 ones are on?
This is just because it makes it easy for me to explain. So it's just a special case. We start everything off with all the loads on. It just makes it really easy for me to do a simulation because of this. Now I look at one time slot later, and what happens? Well, each load, all the loads are on at time 0, and each load flips a coin, and with probability alpha stays on, and with probably 1 minus alpha turns off. That's the model, right? And so this morning I got up and I thought, this is trivial to simulate. This is your homework assignment, it should be. I've been putting off doing the solution for the simulation, and it took me about 15 minutes to write the code. And that's a stochastic experiment doing 100 coin flips. Okay? So basically there's 100 loads there. I could have done a for loop, I didn't, but you could say, you know, for I equals 1 to 100, flip a coin with probability alpha, stay where I am, 1 minus alpha, switch over to state 2, and compare the two. This is random. I flipped a coin 100 times. That's deterministic. It's obtained from that sum. You know, you can barely see the difference, right? Right? So, and you can work it out. I mean, this, you know, mu 1 of 1, you know, for this mean field model, it's the amount of stuff that was in state 3 times the proportion that go from 3 to 1, right? From 3 to 1. Plus the stuff that was at state 1 times the proportion that go from 1 to 1. All right? Well, there was nobody in state 3, so that's 0. And everything was here, that's 1, so I get alpha. Yep. And how many, you know, at the next time step in 2, same thing. I look at how much was in state 1 times the proportion that transferred from state 1 to state 2. That's 1 minus alpha, you know. And then plus the probability of staying still, beta times the stuff that was at state 2. Well, that's 0, so I just get this product. That's 1, so I get 1 minus alpha. Okay. All right, you can do it again. Tell me when to stop. So you can do the same thing. I mean, now you see this stuff in the third state, and you can do the same sort of algebra, and you'll get, you know, basically how much was previously in state 2 times the proportion that went from 2 to 3. All right, and there it is. And you compare this, you go from here to here by doing 100 coin flips. All right? and you can barely see the difference, right? Okay, so I won't keep doing this. But what happens is the mean field model, oh, this was zeta k equals 0. I mean, this is just, just forget about trying to control the system. Just set zeta k equal to 0. You can see it makes it much easier to describe what I'm doing here. Do you notice that the mean field model converges? This is called the steady state, ergodic steady state. So as you look at the mean field model progress, it eventually becomes constant, right? And if you look at the stochastic model, it doesn't look stochastic, does it? With 100 loads, it's just the mean field model predicts the stochastic behavior perfectly, I mean, as well as you'd ever care, I mean, try to find a control system where the linearization is that accurate, or something. I mean, it's just, it's a perfect model. Now, if you zoom in, you'll see it's not perfect. So the probability of being in state 1 is quite small. So the probability of being on for this model is very small. And so you can see, look, it's like 0.01 is the probability of being on. So now I've normalized. Now I've divided by n. N's 100. And you can see there's like a 100% error on that error. Okay, but who cares? That's the way loads behave. They have noise, and we're trying to control maybe a lower frequency component of that. I mean, real water heaters. If you had 100 water heaters and you plotted their power consumption, it would look pretty noisy. Just the normal behavior of water heaters. It'd be awful. So that's that. All right. What? Oh, so this time. Oh yeah, excuse me, yeah. Sorry, yeah, I should have said that. That's time. So it starts off at 1 because both are initialized with everybody on. So the probability of being on is 1. And the probability quickly goes down to this ergodic steady state for the mean field model. It just levels off at a limiting value. And the mean field model bounces around it. I wish I'd plotted mu k of 2 as well, because it would go on to something larger, but the noise would be the same magnitude. Okay, that standard deviation would be the same for each of the states. I should have plotted that. This is the thing we really care about. That's the power consumption. All right. This is meant to mainly just to burn into your brains why I care about mean field models and how they are reliable. Okay. Questions?
So just to make sure, this error corresponds to loads not quite getting as much or too much power that you need.
Oh, no, right there. It's right there. It's at when you flip 100 coins, and the probability of success means staying where I am, is alpha. Right. Then the number of successes is approximately 100 times alpha.
So I'm asking like bigger picture, like when we implement this.
Oh yeah.
When or any time there's that error that is small, what physically is happening?
Oh no, here. I mean, if this is the way water heaters really worked, this would be the fluctuation of power consumption as a function of time.
Which doesn't need to be fixed any more than that. We're allowing for so much. It's okay that the the power is not quite.
Yeah, absolutely. Okay. I mean, because all those pool pump examples, these beautiful plots here. 20 pools, you can imagine how noisy that was. But as soon as you close the loop, it's all gone. And also, here, this is very different. The nominal power consumption is huge, and I'm allowing myself big sways here. And so I can get away with a really hefty feedback loop here to really crush away any noise, just destroy it. If I had something this delicate, if there really was a Kauai water heater like this, their nominal power, this is very much like a Hawaiian water heater where the power consumption is 10 watts. You don't have much room to play with, and so the noise is going to be there. You're going to have, but that's noise. That's the thing, is you're not really creating noise. The noise was already there. just because of the bursty nature of water heaters. Okay.
So the mu Kn, that's from the plot.
Here.
Yeah, this one.
Yeah.
Yeah, so the blue is telling us the proportion of water heaters that are in state 1
Yep.
at every time step.
Yeah.
What about the red?
I should have put the K there. Sorry about that. And the red is the mean field model. You know, the red is up there. Yeah. But I said zeta K equal to 0. So it's so whenever you don't see an N, that means this means the mean field model, which is just taking products of matrices. You know, because here the new, again, think of mu as a row vector. The new row vector is just the old row vector times this matrix. Okay, so to do this simulation was like 2 lines of code, and 3 maybe, I don't know.
You initialize it to be all on.
I just did because it was, you could see why it was, I assumed they were all on, so then I could say now only 2, there's only 2 states you can be in. It made it easier to talk about.
Okay.
Yeah. It was only, I'm not expecting you to do that. Yeah. Yeah, Kauai would blow up if you turned on all the water heaters at once.
So if they're random, then it would convert faster, right?
Well, yeah, I mean, that's a good point. I mean, so if you look at the population of water heaters in Florida, they might be slightly synchronized because we all get up in the morning, we take our shower, at 10 a.m. when we wake up. Just kidding. but those from Honduras too, I don't know. No. Or those from Venezuela, I don't know. But we get up, typical time, I don't know, we take a shower at 8 o'clock or something. And so that makes our hot water heater go to its lower temperature. And so then we cut out and everybody synchronizes. So all the hot water heaters, going to turn on, which isn't very good. And so when you have a randomized pulse like this, you actually have less synchronization. And then they all have the similar dynamics, so they all will cool off around the same. You're going to create some synchronization for a while, but by putting a randomized pulse, you'll have much less. So it only can help the grid, putting in coin flips. It can hurt the load only that you cycle more. So you could end up increasing the number of mode changes from on to off. But again, we've found it's like 15 to 50%. I don't think that matters. Like in these pool pump experiments, there's like 50% extra chattering from on to off. I doubt that matters. Yep.
So how does homogeneity affect?
What's that?
Homogeneity,
Yeah, I'll get to that. So the question is, here I've assumed everybody's the same. Every load has the same transition matrix. I'm going to explain why that's just big deal, not important. But that's pretty deep. I'll give you a main idea. Okay. So now I want to get to control design. So you definitely have to wake up. But I mean for the aggregate, okay? Because like I said, how to design P zeta is a bit outside of the scope of the course. I'll say a few things, but not much. But okay, we've got this, what I'm calling the state process, all right? And that's approximated by this mean field model. And then what we care about is the average power consumption. So U of X is a power consumption when I'm in state X, okay? And that's the thing that the balancing authority really cares about. So the balancing authority would like to be able to choose the zeta t here to make y of t go up and down like I've showed you. Okay, so it's a nonlinear state space model. So it's linear, the model here is linear in the state. I'm thinking of mu as the state. So like in that silly example, the Kauai water heater, it's 3-dimensional because it's 3 entries, okay? And so I've got a matrix vector product there. That's a linear operation, so it's linear. But naturally, it's nonlinear in zeta. It has to be. It's impossible to make it linear in zeta. It's just, if you think about it a bit, linearity means you have, this is positive, this is bounded by 1, this is all sorts of things. There's so many constraints, it has to be nonlinear. So linearization is the trick, and so this course is really great because I'm forcing you to review everything you should have learned in an undergraduate control course. And the very first thing they should have taught you by week 2 is that no system is linear, and you end up linearizing it before you start. And it just turns out that these models are really easy to linearize. Okay. So how we got this beautiful tracking was to actually look at a linearization of the mean field model and then design the PI control based on the linearization. So we're able to choose our crossover frequency, all that stuff based on the linearization. All right. Okay, so this is 2 examples of this design that I talked about. Is that too small now? So basically, there's 2 Bode plots here. One of them is based on my pool, which has a 12-hour cleaning cycle. And the red one is based on Bob Moy's pool, which has an 8-hour cleaning cycle, but randomized. So we basically put a window around the nominal behavior and put in that randomization. And I'm having to find a linearization yet. I'm just showing you what we will get. You're going to get basically a flat response and this massive resonance, and then it's going to decay off. And I put a question mark there. Why do you always get a resonance? And why is the resonance the same whether it's an 8-hour cleaning cycle at 12? Now, by cleaning cycle, I mean 8 hours on and then 16 hours off. So 8 hours on, 16 hours off. Pool, standard pools go on at 10 a.m. and they turn off at 6 p.m. or something like that. There's a clock like that. And anybody have a guess what that is? Think about it. All right. So the way we get this Bode plot, we get a linear model of the system is, first of all, this is a thing that I've been pushing, today, that this guy here is really accurately approximated by the mean field model if you've got 100 loads, say. But then I want to linearize this nonlinear system, which means I want to, even though this is a nonlinear function of zeta, I'm going to approximate it by a linear function of zeta. And that's what's done in control all the time. All right? Okay, so anybody have an answer to this? Besides you, or some of you know the answer. Sort of delay. Well, take a look at this again. Remember, I'm on for a while, and then I turn off for a while. And then I'm on for a while, and I turn off for a while. So think about the normal pool. I'm on for 12 hours, off for 12 hours, on for 12 hours, off for 12 hours. It's completely periodic. So what's the question mark?
The sum of the delays?
Yeah, no, so the nominal behavior is periodic. Yeah, it's a period. So that peak there is exactly 24 hours, because the normal behavior is periodic with, it's approximately periodic with a period of 24 hours. If you watch those histograms evolve, eventually it'd converge, but you'd see some oscillatory behavior for quite a while, and eventually settle down. So it's got this it's got, it has to have, the linearization is going to have complex eigenvalues, Okay. Because I can't do this. We're talking about math now. Okay. So how many of you have seen a small signal analysis before? You have. Like linearization, like how you take a nonlinear system and linearize it. No? Boy, your control professors let you down.
They hide it under different names.
Oh yeah, so what else would they call it? But I mean, you must have seen a nonlinear system, and you still can design a control system.
Building an amplifier and
Yeah.
signal model.
Yeah, small signal models for amplifiers. Yeah, yeah. No, okay. So anyway, okay, so basically we have this equation here. And again, because you're all with me, right? That is vector matrix multiplication if mu is considered a row vector, you know? I mean, this is basic algebra. We definitely had a matrix prerequisite for this course. If you want to multiply a row vector times a matrix, you multiply on the left, and you take a sum. Okay, so I can use this shorthand, you know, if everything's a row vector. And what I want to do is approximate by a linear system, but you always look at deviations. Okay, so assume. Let's see. Well, I'm going to make a bunch of assumptions. So when I talk about small signal analysis, and whenever you talk about linearization, either assuming the input's small or the difference between that input and some nominal input is small. Okay, and in particular, what happens if it's 0? If zeta k is 0, I'm going to give it a different name. So what I'm going to do is look at the deviation between these two guys. You know, what happens when no input is applied compared to what happens when an input is applied. But I'm going to need another assumption. I'm going to assume that these converges. So in the homework, I gave you a formula for how to compute this. We saw this happening just a moment ago, right? There it is. See, those are the mu k's, which evolve according to this formula. And this was all with zeta k equals 0. You know? So that mu k that I'm calling there is really pi k here, because zeta k is set to 0. Right? So there's an example of ergodicity, and you see it's damn fast. Basically it looks like after about, I don't know, I think that's about it. You know, you basically wouldn't see any changes after about 10 iterations. Okay? All right. So that really helps. So it's really a mild assumption. Markov chains are ergodic under minimal assumptions. It's always true. So that's not really an assumption. It's and we're going to design it that way, and we're going to design the nominal behavior. Okay, so then what we're going to do is look at the difference. And I guess I have to turn this off. Bummer. And there's so many ways to define this. In my notes that I'm going to share with you, I looked at the difference between these two guys, and now I kind of regret that. Like, I wish I would, but it doesn't make any difference. Let's just do it. I mean, I've read many papers on this, and I think you can see both definitions used. You can either take mu k minus its nominal behavior at 0, just steady state, or you can look at the control-free behavior, subtract out the control-free behavior, which is time varying here. Either one, you'll get the same model, so it doesn't matter. And I'm going to assume it's small. What more do I have to assume to make sure that's small? Let's see, I'm assuming this is small. So that evolution equation and that evolution equation are almost the same. But you need one more thing.
P is not changing.
P is not changing too much. And also, yeah. So my assumption, yes. Well, not P really, but I don't want this changing too much. I'm going to assume that mu k, mu 0, I mean, is close to the steady state. And that's why it really doesn't matter if you look at the deviation from pi 0 or from pi k. All right? But let's stick to that. Okay, so what are you going to do then? I need an evolution equation for the deviation, and that's what I'm going to get a linear model for. So remember, U of x was the power consumption when